Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. Now, these lectures are delivered for the applied electronics students, and in this lecture I will be talking about the thermal properties of materials and also partially about the crystal structures, in the sense the reciprocal space and the Brillouin zone. So, the contents of this lecture are as follows: reciprocal space, Brillouin zone and their importance, specificity of solids, classical theory, Einstein's model and Debay's theory. Now, in the previous lecture also I was talking to you about reciprocal lattice vectors. Now, we all know about lattice with regard to crystal structures. How do you define a crystal structure? You have a ordered network of points that you call as a lattice, then you attach bases that gives the crystal structure, that all of you know, a network of points. Now, these network of points are connected or can be described in terms of primitive translation vectors. This we are talking in direct lattice. Now, define what are called the reciprocal lattice vectors, capital A, capital B, capital C, by the relations 2 pi times B cross C by A dot B cross C and 2 pi times C cross C A dot B cross C, and this kind of cyclic relations we can have. Now, by translating these vectors capital A, capital B, capital C, they are the primitive translation vectors in the reciprocal lattice. By translating these vectors, a reciprocal lattice can be obtained. It will again contain a network of points. I show only one point here, which is the center, then there will be another point here, at all the blue lines. When the lines end, there will be lattice points. This I call as the reciprocal lattice. So, imagine that all the blue lines end up with this kind of red circle, then that is the reciprocal space. In the reciprocal space, one constructs what is called a Brillouin zone. It is a 2-dimensional space which I am showing. Now, how do you construct a Brillouin zone? Now, you take the perpendicular bisector for this line, bisect, and then it should be perpendicular, and so you have a perpendicular bisector, right? You got a dot here and you got another dot, should be having another circle here. This is the reciprocal lattice. Now, you take the midpoint, at the midpoint you draw the perpendicular to the line. So, you have got a perpendicular bisector and another perpendicular bisector, and so you have to have the perpendicular bisectors drawn, and the area covered by these red lines, the area covered is called the Brillouin zone. Now, in 3 dimensions you will be having this kind of Brillouin zones. They are very important. If you look at FCC lattice, this is called the FCC, as all of you know by now. You have got atoms at the corners, atoms at the face centers. This is FCC lattice. For the FCC lattice, this will be the Brillouin zone, right. What is Brillouin zone? For this is the direct lattice. Now you have to go to the reciprocal lattice. In the reciprocal lattice, you have to construct the Brillouin zone. The way in which it is being constructed in 2 dimensions I have shown, a similar thing should be done in 3 dimensions. You have to construct a reciprocal lattice in 3 dimensions and then take the perpendicular bisectors. The enclosed volume is known as the Brillouin zone. For all FCC lattices, this will be the Brillouin zone. It is something like the bigger size cell drawn in the reciprocal space, it is called a Brillouin zone. So, in the reciprocal lattice, the perpendicular bisector on the line joining the neighbors from a point or joint, and the enclosed volume or region obtained from this construction gives the first Brillouin zone, right. This is the first Brillouin zone for a FCC lattices. Similarly, you have got for a BCC lattices, this is the Brillouin zone. For a HCP lattice, the Brillouin zone enclosed by this is HCP lattice, right. Okay, you got a hexagonal plane, bottom hexagonal plane, and then you got a volume here, right. There will be 3 atoms in the center in direct lattice, but the volume enclosed by these plastic sheets that you have got here, blue in color, this is the Brillouin zone for the HCP lattice, right. Maybe one takes hours and hours for calculating the properties of electrons and phonons in solids by looking at the Brillouin zone. The Brillouin zone should be carefully looked at. For every k point in the Brillouin zone, the energy of the electron or phonon will be determined. And in principle, the importance of Brillouin zone rests with this kind of figure that one gets for the electron in a solid. The solid may be a metal or a semiconductor or an insulator. In principle, for a electron moving freely in a solid, right. You know, for the electron in an atom, now you know for the hydrogen atom there is only one electron that will be in the revolving in the first orbit, that is the K shell. Then the energy is given in terms of N. Now the same N cannot be used for describing electron freely moving in a solid. So the N will be replaced by what is called the wave vector K. Now this is the wave vector K that you have got here. Now the wave vector K is nothing but the points in the Brillouin zone. You have got gamma here, X here, and similarly here gamma here, X here. Okay, this is for copper. This is the Brillouin zone. This is the Brillouin zone for copper is crystallizing in the FCC lattice. This is the Brillouin zone for copper. If I want to know the energy values of electrons which are found in copper, then the energy values will be given in terms of the points in the reciprocal space or in the Brillouin zone. The volume in the reciprocal space, for every k point I can find the corresponding energy values. You see here gamma here, X here, these are some of the notations used for describing the special points in the Brillouin zone. Now the points are shown here. This is the energy as a function of k. Now k becomes a quantum number, it acts like a quantum number, and so this is the EK curves, the energy momentum curves for describing the electronic energies in any solid, here in the case of copper. So you should understand the importance of Brillouin zone. Without a Brillouin zone, it is not possible to show the presence of energy gaps in semiconductors. Similarly, for electrons and energies in all metals and other systems, alloys and so on. Let me restate the importance of the Brillouin zone. The energy of the electrons and phonons. I will be talking in the lectures to come in this chapter about phonons. In the next chapter I will be talking about the energy of the electrons. The energy of the electrons as well as phonons can be described only in terms of k, not as a function of n. For electrons and atoms, the energy can be given in terms of n. N is a good quantum number. N cannot be used any longer in a solid for describing electrons or phonons in a solid. On in the place of n you have k. K is a point in the Brillouin zone. So, the electronic and phononic band structures are very important to explain the various physical properties. I am going to explain the thermal property of solid using the phononic band structure. Similarly, the electron phonon interaction decides the superconducting behavior. Now, with this we come to the end of talk with regard to the reciprocal space and Brillouin zone. Now, we move on to the thermal properties of solids, and especially we will be concentrating on the theories of specific heat. You know, the specific heat of water is 1. So, specific heat is the whatever that you are you know about specific heat, that is the one that I am referring to here also. When you go to the case of solids, it was observed by Dulong and Petit that the specific heat of all solids is equal to 3 R. That is, in the year 1869, Dulong and Petit gave an empirical law stating that the specific heat of all solids should be equal to 3 R, where R is the universal gas constant whose value is, now this 3 R will be 6 calories per degree per mole, right. That is the value of specific heat, which will be denoted by the letter C with a suffix V, right, CV, that as you have here. Now, let us try to understand whatever Dulong and Petit have stated in terms of classical theory. Now, what is the classical theory? Now, you take a solid. In a solid you will be having, let us assume that there are n atoms, and each atom will be having 3 degrees of vibration. You can, supposing it is vibrating like this in this direction, then you can take 3 components in an arbitrary direction. You can take 3 components, one along the x, y and z directions. Now, therefore, for n atoms it is equivalent to 3n harmonic oscillators. According to the classical theory, the energy E will be equal to k T. The energy possessed by every oscillator will be k T. For 3n oscillators, the energy will be 3n k T. Now, n k will be equal to 3 R. N k will be equal to 3 R. R is the universal gas constant. Okay. So, there will be 3 R T. What is the specific heat? How do you define that? You define specific heat C V as the derivative of the energy with respect to temperature. C V is d E by d t. So, you have got E here. So, C V will be d E by d t. So, this T will vanish now, giving rise to 3 R, that will be equal to 5.96 calories per degree per mole as expected by Dulong and Petit. So, the Dulong and Petit's law can be explained on the basis of the classical theory. But the important thing that should be noted is, this is what is happening at room temperature. But as you go down to low temperatures, the specific heat begins to decrease. The value of CV is not a constant like 5.96 or 6 calorie per degree per mole at all temperatures. When you go to low temperatures, it starts falling off, and finally at T equal to 0, CV becomes equal to 0. Now, this variation of specific heat with respect to temperature, as you see here, you can have CV here. CV remains almost constant at up to 400 Kelvin. Then what happens now? When you go below room temperature, then it falls off and ultimately it becomes equal to 0. So, the variation of specific heat with temperature cannot be explained on the basis of the classical theory. Let us have a short break at this point, and we will resume the rest after the break. Welcome back, and I was showing you the variation of CV with respect to temperature. Now, this variation is not explained on the basis of the classical theory, because the classical theory does not contain any temperature term, right. The specific is shown to be equal to simply 3R. There is no temperature dependence. So, obviously, the classical theory cannot explain the variation of the heat capacity or the specific with respect to temperature. Okay. So, we have to now try to do something else. Now, we are dealing with atoms, they are vibrating. Now, it is the year 1901 when Max Planck talked about quantum oscillators, that is a quantum theory was developed in 1901, and you have studied the harmonic oscillator. So, the atoms in solids are vibrating, that all of you know the atoms are vibrating, and at the melting point the bonding is broken and the spring is broken, or the spring constant becomes 0 and so on. The atoms which are held in a solid tightly at low temperature, when you go to high temperature the bonds are broken, the solid is converted to liquid. But the point is the atoms are vibrating. Okay. The atomic oscillations or vibrations ought to be taken into account. So, the quantum theory was used for the first time by Einstein for solids. It was Einstein who introduced the quantum theory to explain the solid state behavior, or particularly to explain the thermal property of a solid. So, Einstein proposed a new theory in 1906 based on quantum theory. He assumed the solid to contain n atoms. They are equivalent again 3n harmonic oscillators as is done by in the classical theory. So, n atoms will be equal to 3n harmonic oscillators, and the most important point is Einstein assumed, for the sake of simplicity, or at his time he thought all atoms should be vibrating with the same frequency, right. So, the important point is all the atoms were assumed to vibrate with the same frequency nu, or you can have nu suffix e, it is called Einstein frequency, right. Einstein assigned the same frequency for all the atoms. For the average energy calculation, the oscillators are treated according to Planck's theory. The quantized energy values of atomic oscillator are given by E n is equal to nh nu. You all know, according to quantum theory proposed by Max Planck, the energy eigenvalues E n, they are simply equal to nh nu, where n is an integer, h is the Planck's constant, nu is the frequency. This is what you have studied, I mean according to the quantum theory given by Max Planck. Of course, it is called the old quantum theory, because according to the linear harmonic oscillator that you study in quantum theory using the Schrodinger equation, it is not nh nu, but it is n plus half into h nu. Okay. That n is not exactly n, it is n plus half, and if you talk of this half h nu, that is the minimum energy that the oscillator can have, that is called a 0 point energy. Now, let us not now be concerned about that extent, but let us assume this value. Then what Einstein got for CV is the following expression: the specific or constant volume, that is CV, is equal to 3 times R e to the power of x into x square divided by e to the power of x minus 1 to the power of 2, okay, where x is equal to theta e by t. I told you theta suffix e, it is called a Einstein temperature. T is the temperature which is variable, right, from 300 to 0 Kelvin. You want to study how the specific varies. Now, the important point is the temperature dependence is coming here, right, because through x the temperature dependence comes in the low temperature limit. As x becomes large, okay, x becomes large means T is low. At the low temperature limit, when x is large, e to the power of x minus 1 can be treated as e to the power of x, or the bracketed term becomes x square by e to the power of x, you have got e to the power of x square, you have got e to the power of x in the numerator, in the denominator will be having e to the power of x square. Now therefore you will be having this term will become x square by e to the power of x, because the one has been omitted. This entire term will become simply x square divided by e to the power of x, and the limit of this expression is 0 as x increases. So x increases means when t becomes smaller and smaller, t tends to 0, Cv will be tending to 0. You find that a specific heat that you have got here, that is measured as a function of temperature, you start from something like 250 Kelvin. The continuous curve that you have got here is due to Einstein, right. The continuous curve that you have got is due to Einstein, wherein the important point is there is a exponential dependence. I showed the exponential right term, and the temperature falls in this manner. There is a exponential dependence of Cv with respect to temperature. Now if you look at this line, there is another line that you have got here. See the experimental points here, right. The experimental points are there, that is a specific heat measured as a function of temperature. Dots are shown here, and more or less obeyed what we will be calling the Debay's theory, or in other words I will say, you see the experimental curve, there is a deviation between the experimental observation and the Einstein curve. So in the case of Einstein's theory, the temperature falls off exponentially, unlike the kind of behavior that you see experimentally. Experiments indicate that the specific heat follows a T cube law, right. It is a T to the power of 3, right. Cv is proportional to T to the power of 3 and not a exponential dependence. The plot shows the heat capacity variation. In the case of silver, the y axis is in the heat capacity, calories per Kelvin per mole. In the case of the units of 3R is 5.96. Over the entire experimental range, the fit to the Debye theory is excellent. Now what is Debye theory? The one that we are going to see now. Why should you go to Debye theory? Because of the fact that as at low temperature it correctly recovers the T cube dependence, and at high temperature it converges the Dulong and Petit's law. At higher temperature it converges to the Dulong and Petit's law, and again as the experiments indicate, and at a lower temperature it obeys a T cube law, and that is the kind of variation that one observes experimentally in the case of silver, not only in the case of silver and in other metals and alloys as well. But on the contrary, what about Einstein's theory? The Einstein theory shows a marked deviation from the experimental curve. The experimental curve is here. The Einstein theory shows a considerable deviation. So we have to drop the Einstein model. The Einstein's theory of specific has got a demerit, namely the heat capacity falls off exponentially in the low temperature limit, unlike what Debye has showed in the later years. Now therefore, because of the deviation between the experiments and the theory and Einstein's theory, we have to look at some other model. The other model is given by Debye, and so let us move on to the Debye's theory. Before we go to Debye's theory, let me point out the demerit of Einstein's model. Einstein's expression has an exponential dependence of the specific heat on temperature. It makes Cv to fall off more rapidly compared to what is observed experimentally. These are the experimental dots. The dots are experimental points, right. Now the Einstein theory shows drop which is faster than what it should be, right. This is the actual value. On the other hand, Debye's theory, it shows a good agreement, right. That is the reason why we agree with the Debye model. And anyway, as on date we have to go beyond Debye model. We have to talk about phonons and lattice vibrations, phonons, and what else. The energy of the electrons and phonons can be described only in terms of the points in the Brillouin zone. That is the connection between the thermal property which I am discussing with the Brillouin zone. Now you will understand the importance of the Brillouin zone. I come back to those things at a later stage. At present, I should make the fall is more rapid than what it should be. Experiments indicate a TQ behavior at low temperatures, but on the contrary, the Einstein model showed a exponential behavior. Fall was too rapid rather than following a TQ law kind of behavior, which is shown by Debay's theory. So, Debye model is in a better agreement. Now, what is Debay's theory? We say that what did we do in Einstein's theory? So, Einstein had a solid in which there are n atoms. Now, each atom, the n atoms will be equal to 3n harmonic oscillators, right? And Einstein assumed all the atomic oscillators to vibrate with the same frequency. The important point is he looks at the atoms, right? Specifically in the atoms, the concentration is on the atoms. On the contrary, Debye considered a solid as a continuum. It is something like a elastic medium, and or you can have a string, you can have a thread, and you can make the thread to vibrate. Now, you can have one loop or two loops, and so different vibrational modes. If you have got one loop, the wavelength will be having a particular value. If you have got in the same length, suppose I vibrate and I get two loops, as you do in some experiments like Kunst tube, you can see the loops, right, the number of loops. So, you can have in the same length of the one dimensional solid, you can have one loop or two loops or three loops, depending upon the number of loops, the stationary waves that you got, the wavelength will be different or the frequency will be different. The point I want to stress is, instead of considering all atoms to vibrate with the same frequency as was done by Einstein, now Debye considered the solid as a continuum, and he tried to calculate the possible vibrational modes or the vibration frequencies. So, according to Debye model, the continuous solid will be vibrating with different frequencies, right, different possible modes will be there. Let me now summarize. The reciprocal lattice vectors are obtained from the direct lattice vectors. I showed the relationship. Brillouin zone is nothing but the Wigner sized cell in the reciprocal space. Brillouin zone is of considerable significance because of the fact that the electron energy as well as the phonon energy, all these things can be given only in terms of the points in the Brillouin zone. The classical theory with regard to specific heat, it is able to explain Dulong and Petit's law. The variation of the specific heat at low temperatures could not be explained by Dulong and Petit's law. So, Einstein attempted to explain the variation of specific heat with respect to temperature using his own model. The questions for this lecture are as follows: what is Brillouin zone? What is its significance? Give the numerical value of the specific heat of solids according to classical theory. How was the above problem tackled by Einstein? With this we come to the end of this lecture. The remaining things will be dealt with in the lectures to come. Thank you.